Nothing much. I'm just waiting for this to work. Is this working? Working yet?
Just starting everything up?
Yeah. My horizontal. Oh, okay. Now it's working. There we go. Okay.
Bozio mój nachuj.
What does that mean? What language is that? Sensation what?
You tell him.
Oh, that's Russian.
Yeah.
What's up, Sib?
It's sort of. I think you meant to say no, not really, but it sort of sounded like Russian. Fucking practice.
How do you say no in Russian again? Da is yes. What is no?
Niet.
Niet. Niet. Thank you, Jeff. Jeff said it too. Yeah. Niet.
I guess everybody knows.
No. No.
How do you spell it?
Yo, you need a Russian soundboard.
I need a Russian soundboard. I thought about like having something where people could redeem like me to change my soundboard to like the geese or something. I don't know, like something crazy. Something silly.
Just have loads of Obi-Wan Kenobi stuff going on.
Yeah, you were trying to do the hello there. Did I ever have that? I don't think I ever had that as a command, did I? The hello there? Oh, I know what bot you're talking about. But that one, I don't think that one works on YouTube. Yeah, you're talking about Enigma's bot, right? I think it's only on Twitch. Yeah, where is it?
No dice.
No dice. Anyways, yeah, today's Tuesday. Yay. Made it to day 2. We had a fucking heater of a stream yesterday. Holy shit. Dude, I had to take like a nap from like 7 p.m. to 8 p.m. because I taught it. I did my UCLA lecture, right? 12:30, 1:45. Then I went quickly to go drop my car for like some recall bullshit. And then we were streaming 3 to 6. And then I think I had another student I had to teach. Yeah, right. 6 to 7. And then I just went to bed from like 7 to 8:30. I was like, my brain needs to stop. Only so much I can take.
See, I'm jealous of people that can do that.
What, take naps? I love naps.
Yeah, my brain is either on or not.
Nah, dude, I'm the king of naps. I made the fatal mistake in AP Calculus in high school of learning how to like fall asleep during lecture, and it screwed me, dude. For the rest of my academic career, once I figured out how to fall asleep in class, anytime I would like get to a class where I was either like checked out or like I didn't understand it, neurons would start firing me like, all right, time to fall asleep.
Night.
Yeah. I remember in high school, I was like, yeah, I want to learn how to fall asleep in class. I think that'd be a cool skill, you know, because I knew everything in AP Calculus in high school. It was cake to me. I didn't really need to pay attention, but this screwed me in college because you do need to pay attention in college. But I had learned to just fall asleep, so that'll get you.
Those naps that you wake up out of 10 hours later is diabolical.
Yeah, that's not a nap, dude. That's sleeping.
You go to sleep, you wake up at 8 p.m.
Yeah. Okay, let's see. Okay, for my UCLA people, are there any specific questions you want me to go over? Office hour stuff? Please let me know. I'll put it first in the queue. Otherwise, I know we have a long list of other things I can do. Nick, we could just like do fun stuff with your what is it? What exam are you trying to be? A something worker. A what worker?
Court officer.
Court officer. Officer of the court. That's pretty cool, actually. What's a court officer?
Those who protect the judge and sometimes stand outside of the court so nobody goes in.
Oh, these people. So wait, are they police officers or they're separate from the police?
I think
they're separate from the police.
They're more of peace officers.
Peace officers. That's good. Rather than like not peace officers. Okay.
I'm never really gonna distinction.
They're allowed to
this girl's kind of cute.
carry firearms.
Okay.
They can carry firearms. They can arrest. Stuff like that.
Okay. Nice. Sib's got a good question. Cool. Thanks, Sib. Got it. Okay, Mr. We'll go through this too. Asa says, I was just here because you had mentioned about going over to integrate Gauss's law and what it means. Super confused about this stuff. Sure. What part about integrating Gauss's law? I said so many things. Let me see what they're... Yo, what's up, Ethan? Haven't seen you in a hot minute, dude. How's life, bro?
Well, I mean, like, I feel like life's going on the uphill for me right now.
That's good, dude.
Okay.
Yes, big claps. Good job. What's up? You want to tell us, give us a little story time. What's going on while I find, like, what this thing with Gauss's law is?
I guess, yeah. I guess, like, I wouldn't mind giving, like, a little background of what has happened.
For a little bit of background, Ethan's been in our Discord and whatever, our servers for, what, probably 3 years at this point? He lives in Belize.
No.
And he just graduated high school.
Yeah, I mean, like,
Fire.
Yeah. I feel like it's been like 4 years, maybe 3.5.
It's been a lot.
About
We've seen you grow a lot, which is great. We love that.
It's already not on so much. It's just work is, in my way.
Work is in your way. Okay. Work keeps you busy. That's a good thing.
But I mean, hey, I still make some money at least.
Making money is great. Yeah, love that.
But yes, I'm just letting you know. Just last week Saturday, I just got into Denver of the U.S.
You got into? Oh, you're in the United States. Oh, that's cool.
For now.
Oh
Just
man,
for
I was
2
in
weeks,
Denver
but-
like 2 weeks ago, dude. Yeah, I was so
I'm
close.
here.
Good. You're in the U.S. right now?
Yeah,
Jeff says, hey, I live in Denver.
Denver and Colorado.
Okay, very cool. I was just in Denver like 3 weeks ago. I was playing a show there or something. That's very cool, man.
But I mean, hey, I was preparing. I got some school materials. I
Good.
got like puzzle books, school supplies, clothing, shoes, like lots of stuff.
Good, dude.
And while that is good, I have some free time right now. You're still doing that one random tournament thing that I heard about last time?
Yeah, we're doing a little summer tournament. Yeah, we're doing yeah. We did Fortnite last weekend. I'm out of town this weekend for like some wedding stuff, but the weekend afterwards, yes.
Wait, are you going to do a game after this? Like,
no, not after this. No, it's always on the weekends. Games on the weekends. Yeah. Oh, Asta, was this what we're talking about? Was this the stuff that was confusing? Or are you just talking about Gauss's law in general, Asta?
well, I can still ask a question?
Oh, yeah. So, Ethan, I'm teaching a class at UCLA. And so a lot of the UCLA students come now to office hours to ask questions about physics. Yeah.
Okay. I mean, I do love physics, but...
Sick. We'll hang around. Learn some stuff. Yeah.
Well, I want to ask a question, though. Like, a question to at least get something.
Oh, yes. Ask that a little bit towards the end. I gotta help out the UCLA students first because they're like my job. But I'll be
screenshots.
Yeah, posting the screenshots. You know where it is. Yeah.
Excellent.
Okay, cool. Okay, here. Let me explain Gauss's law real quick to some people. Which is maybe I think probably related to this, right? Okay, so let's see. So here it says, positive charge of 12.5 nanocoulombs is placed at the center of a 1 meter wide cube. Calculate the electric flux passing through the right face of the cube as shown in the figure below. Okay, that's cool. All right. So, yeah, I mean, Gauss's law deals with flux. And so, flux is equal to the electric field times the area that the electric field is going through. And so usually what we do is because electric field and area are not really like constant, or like maybe like the electric field varies as a function of the area, or maybe the area isn't just like a nice shape. So what we end up saying is this is the integral of E dot dA. Okay. And then if E is constant, okay, if the electric field is constant everywhere along my dA, along the area I'm looking at, this is the same. You can pull it out, and this is just integral of dA. And actually, yeah, someone corrected me earlier. This is technically a surface area integral. I think they put SA. Here's what they do. I don't think followage works. I don't think I have any of these. Yeah, chill. I don't think I have any of those commands. Y'all spamming my chat. Okay. All right. And this is also equal to, right? Let's remember that electric flux juice. No, god damn it, sensation. Not the right one. Is equal to Q enclosed over epsilon naught. So this is the important thing. Is that the electric flux anywhere. So as like I get further out, right? I start covering more surface area, but my electric field goes down. So this would go up, this goes down, but the amount of charge you're enclosing is always in the center the same. Yeah. Oh, does that really work? Time Denver? Wow, that's a cool command. Abu says, how difficult would the final exam be in comparison to the midterm? Probably about the same. I try to not like just like slam people with things. That's not nice. Okay. So for this question, right? We know it doesn't really matter what surface I create to enclose this charge. It could be a cube. It could also be a sphere, for instance, right? The integral of the electric field times this surface area has to always equal the charge enclosed over epsilon naught. Okay. Okay. Right, and then this is equal to this. So, with this, what physics is? This is E&M college. So, with the cube, right? We're only looking at the flux on 1/6 of the area, right? If I added up all the flux from all 6 sides, that should equal the same amount of flux from like a big sphere surrounding it. It's all the same. Okay. Also, I'm still a bit confused about the whole enclosed charge idea. Like, how should we think of the field form? Like, I still don't really understand why inner field for conductors is 0. Yeah. Okay. Okay. So if you have a conductor, right? And the charges are all here. Okay. Remember that your electric field is equal to the potential divided by the distance. Okay. In this case, the potential difference, or I think we say this, we say delta V over D. In this case, the change in the potential between these 2 points is 0. So there is no electric field. In order to create an electric field, you need positive charges on one side, and you need like a different charge on the other side. That could be like negative charges. That could be 0 charges. For now, we like usually assume like negative charges. You can always pull E out as a constant if it makes sense in terms of geometry. Okay. So this is what creates E field. So if you have like positive charge and positive charge, then I don't think there is an E field in between these two things. I think you need a change. You need a difference in charges or a difference in potential to create electric fields. By this, right? If there's no change in potential, then you have 0 electric field. Okay, so sorry, I gotta find my YouTube chat just separate. Where is it? There it is. No, not that one. Okay, there we go. Let me just read this. Okay, Fedekai says, I think I'm still confused on how to set up integrals for non-uniform charge densities for line surfaces and volumes and their connections with each other. Okay. Sib says, it's confusing to see where the area vector would be pointing in the different faces of the cube. It's actually not that bad. So here, let's... In this one, right, here's where dA would be, Sib. This would be dA, right? These would all be dAs. These are all area vectors on this side, okay? The issue is that the electric field is perpendicular to it here, right? But then it's like not perpendicular here, and it's like not perpendicular here, right? The electric field from a point charge radiates out in a spherical pattern. Okay. So if you were to like independently figure out every little like E here and every little DA, that would suck. That would take a lot of time. So what we actually do here is we use the flux trick, where the net flux through a surface has to be equal to the charge enclosed divided by epsilon naught. So if you're enclosing 1/6 of the area, and all of the area things are like symmetric about each other, right? Then you're gonna get 1/6 the electric flux through it there as well. So I believe this one for this E is equal to 12.5 times 10 to the minus 9 over epsilon naught, and then it's 1/6. No, you're good, Sib. Yeah, this is through Gauss's law. Yeah, this one. This is a Gauss's law trick. Well, I mean, E dot dA is Gauss's law. Again, you could have done this. The issue here is that E dot dA is not constant amongst all dA, right? Because E over here points at an angle reference to dA, and then E over here points at another angle reference to dA. But it turns out that if you were to add up all the different little components, if you went through and did the calculus, it'd be a huge pain in the ass. You don't want to do it. You would get that the total flux here is 1/6 of the total flux across all 6 faces. Yeah. What is the proof? I honestly don't know. That's a deeper level of things. What's the proof to this law? I think the proof to this law is they just do it for a point charge. We did this in class, right? If you have a point charge and you go by, what is it? Everything starts becoming like kind of circular logic, right? Because like F is equal to QE, right? So you could figure out what the electric field is due to the Coulomb force of like some test charge Q, and you know that force is spherically whatever symmetric, and then it turns out when you figure out like E dot dA flux, it also equals Q enclosed or epsilon naught. It just ends up being the same thing. Is there a rigorous proof to it? I don't know. Let's fucking Google it. I don't know. Like,
well, presumably if it's physics, someone's come up with a hypothesis.
yeah,
And then
well,
they've had to make proof.
exactly. Yeah, well, I mean, a lot of times it's like someone comes up with an idea, and they're like, I think this formula fits. And then they test it on a case, and they're like, yeah, it does. And then they test it on another case, and like, yeah, it does. And like, if it keeps doing it, you just believe it.
Well, that's the difference between a hypothesis and a proof.
Yeah. Here we go. What is the proof to Gauss's law? I don't know what the proof is. I feel like the hand wavy proof is to do it for a point charge. But let's see. Let's see what good old ChatGPT says. Yeah, see, they do it for a point charge, right? Okay. And so, oh, okay, it's the divergence theorem. That's the key thing. If you want to get into it, this is the calculus of it.
When does something become a proof? When it becomes a what's that word? Shit. Theory.
Theory, yeah.
When it becomes a theory, it's been proven.
This is the divergence theorem. If you really want to know about it, it's the divergence theorem.
Anything can be proved whether right or wrong. At any given point in time, sure.
Oh,
I mean,
I don't know, like a postulate? Is it like a postulate?
Because postulation is still hyperbole. Wow.
Mm. In theory, the laws of physics could stop working tomorrow, but probably not. Yeah. There's actually also this like key thing about physics that we assume the laws of physics apply everywhere in the universe. Because if they don't, then everything's like screwed up. So yes, the proof is like we do it for spherical, and by the divergence theorem, which is whatever fancy calculus, that applies to any irregular shape. Does not matter. As you know, if you were to individually calculate, as like Asta was saying, E at every single point in the surface, then you would still get the same answer. Yeah. So the trick here, yeah, the trick why you don't want to use E.dA on this one is because E is not constant across this surface area face. But it would be for a sphere, because a point charge has a spherical electric field distribution. And so from that information, you can figure out that, right, EA is Q enclosed over epsilon naught. And then for this one, right, you end up saying, okay, well, 1/6 the area is equal to 1/6 Q enclosed over epsilon naught. So yeah, you wouldn't formally calculate Gauss's law on the surface of, because this is irregular. This sucks. But yeah, when gold comes down. Are we gonna be able to use Gauss's law for every problem on the test? Well, yes. I mean, if you can't, then it gets really difficult to solve things. It becomes next to impossible. So for the test, if we're finding electric field, no matter what volume, sphere, parallel plate, infinite line of charge, you're most likely gonna be able to do it with Gauss's law. You got it. You're all good. All good. Yes. No, that's correct. Yeah, I'm trying to. I mean, you could also find electric field if you're given the potential, though, right? Remember that electric field is the gradient of the potential. So the potential could be given to you as a function, and then you would need to take whatever derivative in order to get the electric field. That's another way to get electric fields. You can get it from, like, if they give you a given potential profile, that works as well. But for shapes, it's almost always going to be either it's a point charge, you use a sphere, it's a line of charge, you use a cylinder, or it's a sheet of charge and you use, like, they call it a pillbox, which, I don't know, it's kind of like a weird name for things, but yeah, like a rectangular cube. But that's not too bad, yeah. Do you mind showing how to set up the relations in the field integral? Sure. Yeah. I know, it is confusing, yeah. So like this stuff? Not this, sorry. Yeah, Gauss's law is like one of the first like mind fucks that happens in physics. You're just like, whoa, what? And it is very useful. It is good. It is good to like to stumble a bit and like try to really understand it. It's an important thing. Thank God I'm not teaching you like Biot-Savart. That gets like even more complicated. You guys want to see what like Biot-Savart law is? That's in 1C, which I mean, maybe I'm teaching you, but yeah, this is even more like kind of like, this is why having knowledge of vector calculus is like really important. But this is what you learn when you do magnetism. You'll learn how to like calculate the magnetic field of like a section of wire that has a current located at distance r, and now it's a cross product instead of a dot product. This becomes not really fun to deal with, so, but that's for later. Yeah, don't worry about that. That's not in this class. But field meaning the chapter before Gauss's law. Oh, okay. Okay. Let me see exactly what we defined electric field as. Sorry. Okay. I think we defined electric field as the force acted upon a charge Q. It's like force per unit charge. That's how we define electric fields. And then we end up doing that with work to then get like potential energy and stuff. Yeah, okay. Okay, yeah. All right, so here was the original definition we had for a field, okay? We said, suppose you have a bunch of source charges, Q1, Q2, Q3, like a bunch of little charges, okay? And they're located at different positions relative to where you're measuring the electrostatic force on a test charge Q, okay? The net force that each of these source charges exerts would be the sum of all the forces. So the picture they give is like, figure it. This is kind of it, yeah. Okay. Okay, you're good. Yeah, you're good, Sid. So if you have a point, let's say a point here, right? And that has a charge Q. You could add up what all the different forces are on it, acting from all these other different point charges, okay? This is the case where, like, it's a huge mess. Like, there's no real, like, pattern to the point charges, okay? But adding up all those forces, okay, you end up getting, like, the total force is equal to the charge on your test charge that you're measuring, the force that's acting on that thing, times 1/4πε0, and then it's all these other things added up together. This stuff here is what we define as the electric field, such that the force on a charge Q is equal to Q times that electric field. And the electric field is composed of a bunch of different point charges. And what we do to write that in kind of like summation form, right, is we say, okay, that's the same thing as 1/4πε0, which this is K, and then this is the sum of all the charges, all the charges creating the field, which is like Qi Ri squared, and then that's in the R hat I direction. Now, summations, this is like a math thing, right? This is quantized. So like you're adding up individual charges. But let's say, for instance, you have, how do you get a value for that? Yeah, R hat points in all different weird ass directions, for sure. Yeah. So if you're doing this also would suck, because you'd have to calculate each individual R, right, for each charge, and then you'd also have to calculate the direction R hat that is pointing, like the vector that connects the charge that's creating the field to where you're measuring the field. And you see how like R hat would be very different for all of these things, right? Each one of these individual charges creates like a new R hat that's going in who knows which direction. But, okay. This is for quantized. This is for adding up little individual charges creating a field. More often than not, we don't have little individual charges. We have like lines of charges. Or we have like a surface of charge. Or we have a sphere or whatever. Okay? So instead of writing this sum as like individual charges, we can say this is the same thing as the integral, okay, of dq over r squared dr in the r hat direction. Yeah. Well, here, I'm gonna show you from the principles of it, okay? So, sorry, not dr, sorry. Get rid of the dr here. So we already had dq, sorry. This is what it is. So it's integral of dq, right? Because if you integrate dq, you're adding up all the little individual q's, and then you're dividing it by what the r is for each little bit dq, and then you're making sure it's in the r hat direction. So this integral would get messy if this r and this like dq are not well defined by like functions that are related to each other. But luckily, when we have like lines of charges or sheets of charges, this dq and this r are related. They have like relationships between them that have like some nice geometries and things. So, for instance, when we do this, when we decide to do a line of charges, you don't like my sigmas, dog? Chill. Yes, the R is changing. Correct. So look for instance in this one, Fedekai, okay? So here I have a line of charge, which I can think about as a bunch of little different Qs, okay? And you're correct. They would have like an R1, you know, this would be like R2, this would be like R3, and so forth, right? There's a bunch of different Rs, okay? But what I notice when doing this integral, right? So this is going to be, right? E is equal to K, and we're going to say integral of dq over r squared, r hat, okay? What I notice is that, okay, well, dq, like a little bit of charge here, is the same thing as some charge, linear charge density lambda dx, okay? And then the r, right? So the vector that connects where like my dq is to where I'm measuring my electric field, okay? That r also depends on x. Because what we found here, right? If this is r, this is z, and then this is x, you figure out that, oh, well, r squared is equal to z squared plus x squared. So now for this, you end up being able to substitute it as k, brain nourishment, yeah, nice. This is going to be lambda dx, and then this is over z squared plus x squared, okay? But in order to deal with the r hat, I agree, this is problematic because the direction is changing, right? Connecting to here, depending on which little bit of the dq I'm looking at. What I notice is that all of the directions in one side pointing to the right, that component will cancel out all the directions pointing to the left from the right. And so all I really care about in terms of r hat when adding up my little like bit of electric field from that dq is I only care about the z direction in this case. And that's why we end up saying that, oh, well, all I really care about is e cosine theta. And then that's going to point in the z direction. Because let's think about this little bit dq, right? That has components, right? It has a component of the electric field that's in this direction, and it has also a component in the electric field, a component of the electric field that's in the y direction. And if we want to figure out only this component, because this component will cancel out with this component later, that ends up being whatever this is, the total e cosine theta. Like, the problem for this question in particular is that I have to be very intentional with recognizing that, yes, you do, 100%. This is not something you can just, like, run-of-the-mill just be like, oh, well, I think it might work. I get confused when I can make a simplification. Yeah. The trick to that is you have to recognize patterns. And this is all a lot of classes are, honestly, but like physics is especially like this. It's you're recognizing patterns and like shapes, and you're like, okay, when things look like this, I do this. When things look like this, I do this. And the only way to get that is practice. That is, some people have some sort of natural intuition that they can just like see things and be like, oh, well, it's got to be that. Other people, like me, have to have seen enough examples that I know that I can recognize it looks very close to something I've already done. And then I can try to apply the same trick, make sure it's valid, and then solve the problem. So Yeah. Asta said this is only applied for a line. This specific example is just for a line of charge. But it creates a cool symmetry where you just get a field in the z direction. You can do this for there are other like well-known cases. So this is, if you go in the textbook, these are very good here. Do you see how it says now for an infinite line of charge? This is the one we had to fix, right? This one was wrong. But this is one case that gets brought up a lot. The other one can be due to a ring of charge. So this is another case that is cool. So now this is a 3D shape. Okay. Is it in this chapter? The one Fedekai is the one you have questions about? Then we have infinite planes. Do they do the infinite plane here? Do they not? They don't do it. What? Where's the surface charge one? They do it for a disk. Okay, well, anyways, fine. So these are all. This is an application of this, right? But now it is like stretched out into 3D, and so now you are going. I say like around in a circle, right? So now you have all of this. And what you end up seeing is that like anything in the XY plane, like any of this stuff will cancel that, that will cancel that. And so this one is only again in the Z direction. But now this becomes like a, now you're dealing with R in like 3 dimensions. Okay. And then if you wanted to extend this now to a sheet, now you basically do this, but you add another integral where you just keep like doing more of these rings as they get further and further inwards. So you're building off of like the generic idea of, okay, here's for a line of charge. Okay, now let's say that the line is a ring in 3 dimensions. Okay, now let's say there's a bunch of rings that make a surface, which is like a, you know, a plate. And it's all about like just taking what you learned last in the previous question and then just adding probably another bound, another like D whatever that you got to deal with. Okay, but let me see. Question 19. Yeah, and don't worry. Like, I know this stuff is tricky, especially since you learned it. You're learning it so fast. It's don't be too hard on yourself if you're not understanding it right away. It takes a lot of time and practice to like really get this stuff. Infinite rings look like a plane. Correct. Yeah, that's true. Okay.
Chuck Norris can tie his shoes with his feet.
Chuck Norris's calendar goes straight from March 31st to April 7th because no one fools Chuck Norris. That's a good one. Ooh, that's cool, Pear. How'd you get that Unicode? That's dope. Okay. Here it says, electric field lines created by 2-point charges. Determine the sign of charge A and the sign of charge B and the magnitude of the ratio. Okay. Is this... What chapter is this in? What are we doing right now? Is this Gauss's law yet? No, it's electric charges and electric fields. Okay. Well, you know electric field lines emanate outwards from positive things. So that instantly tells you, like, B is positive, right? So, okay, cool. B is positive. And that tells you A is negative. Just with the direction of the lines. The other thing you learn is that the density of lines is proportional to the electric field. And by that, so again, if you have like a bunch of lines really close to each other, that means the electric field is strong. If the lines are very spread out from each other, then the electric field is weak. okay? And we know that, right, that electric field is equal to F over Q, where this is like, right, K Q1 Q2 over R squared. So if you have more electric field, you must have more like source charge creating that electric field. Oh, not this question. Oh, okay. Well, anyways, just to explain this one, it's pretty easy, right? You just count the number of field lines. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm guessing this is 25. And that's why you get that it's, yeah, the ratio is 2.5. Okay, which question, Fedekai? Isn't this 19? The charge above a sphere when we asked to do integral. I know it's in the later questions. Okay, well here, you go find that for me. Go find the question. I'll do it. Cool. Ooh, yeah, the thin ring. We did this one. I did this one yesterday during office hours. Who submitted this one? Asta did, yeah. Oh, that is pretty, Pear. I like that. That's pretty. Oh, did I not save? I didn't. Yeah, I didn't save the text for this one. I really should have. Yeah. Yeah, Asta. I will send you the recording for that one because that one took 45 minutes to do. I really don't want to redo that question right now. You're talking about the Taylor series one, right? This one is kind of like it is a huge pain. Well, one second. I can probably actually find it for you real quick. Yeah, look for it. Yes, it was on yesterday's. One second, I'll just get it for you. If I go to YouTube, I know exactly where it was. Live office hours is here. This one. Okay, and then where was it? Was it? Thing. Yeah, bro. This one gets. And giving it we learn about Taylor series. You want to go through all this? Like, subscribe this channel. The next time I'm on. Yeah, we did all this. Where is it? Okay. Is this here? Those positive charges with negative charges, and that creates cavities. Yeah. Okay. Here we go. So here, it's this link. Let me send it to Asta. And then it's starting at an hour and 10 minutes. That's when we started doing the question. I don't think we finished it until like 2 hours. There. I got it here. Question 20 is the one. Okay, Sib says, are we still going to get this until midnight for next week's exam? Yes. Yeah. I'll give the same amount of time for next week's exam. Or not next week's, but the one we do over... Wait, is it next week? Is our exam next week? That's so fast. I think you're right, actually, because then the final is like the week after. Oh my god. I haven't even like... What? I gotta write another exam? Damn. This is a rough class. I understand why professors don't like to teach over the summer now. It's pretty brutal. I know it's brutal from your point because you're learning it, but it's also brutal. It is brutal from a teaching standpoint. It's so quick. Okay, question 20. Okay. Oh, okay. What class is this? This is physics undergraduate, ENM. Okay, total charge is evenly distributed through a plastic sphere. Inner radius, outer radius, cool. Oh. Oh, and are we not allowed to use Gauss's law for this one? I mean, this is really easy with Gauss's law, right? Your final grade definitely depends on the exams throughout the course. Yeah, it does. The weighting, though, Saint, changes based on... So, for instance, some professors have only one midterm for the entire quarter, and then the final is like 90% of your grade, which I think is terrible. I have two midterms, per se, for this one, and they're worth 10% each. The last quarter, when I taught like a regular, not a summer course, I had 3 midterms, and they were worth 10% each. This one, I weighted stuff a little bit more heavy towards homework. Just to like kind of give kids a break. Like, it's more like, what can you do? Was it Asta or Asta? Am I saying it wrong, Nick? Am I saying it wrong? Okay. And actually, I don't really... Well, okay. And they calculate the magnitude of the electric field at the location 0, 0, 1.63. It's like Black Clover. What is that? Is that an anime?
No idea. If you tell me its original title, maybe I'll know. But generally speaking, if it's got an English title, I've never heard of it before.
Sensation only knows the OG ones. It's a fire anime. Okay, that's cool. Nice. Black Clover's really good. Nice. Okay, so I think the spherical symmetry arguments here is that like any electric field from here, right, is going to cancel out electric field from here, and you're only dealing with Z components. And then I think what you're going to do, so this is actually really cool. If you were to do this without using Gauss's law. What is XP? I don't know what that is, Nick. That's just YouTube stuff.
No, I did see this like 5-6 years ago. I barely remember it, but
oh, the anime? Yeah.
It's more. I can't remember exactly. Maybe 7 or 8 years ago.
Oh, you know what this is? This is interesting, actually. This is like a bunch of rings of charge that are like... It's cool. We're going from like... from the center, we're building like more of these rings out. And then there's also like a depth component to it as well. This is a real pain to do. In terms of just straight KQQ, instead of just, yeah, whatever, KDQ over R squared. This is a beautiful example of where like Gauss's law makes this so much simpler. Right? Don't forget to give the stream a like. Yes, Nick. It's okay. Don't, yeah. Let the UCLA students like just exist there. It's okay. Don't bother them too much. Yeah, the R here sucks. For Gauss's law, this is really easy, though, right? Because for Gauss's, if we wanted to do this with, did they ask you to? Yes, all non-Z. Yes, exactly, Saint. Yes, all the non-Z components will cancel by symmetry. The issue is that like now you're having to integrate what the Z component is of each little individual DQ. R hat into a K hat. What are they doing with R hat and K hat? Here, let me see. Where's my thing? There we go. All right. K hat is the Z component though, right? Yeah, what you're saying, which is similar like to what got said in this one, Fedekai, is that for every R hat here, all I really cared about was the Z component of it, because everything in the x hat. So r hat is composed, right, of x hat plus y hat plus z hat, right? There are 3 components that make up r in 3 dimensions. But what we said is that, oh, well, all the x hat components cancel each other out, so I don't care about them. And all the y components, well, this is a line of charge, so we don't really care about anything in y, so that's also 0, right? So r hat now only refers to z hat because it's simplified. In this case, with the sphere, right, it's the same thing. Anything in the x hat direction for r hat is going to go away because it's going to be canceled by an oppositely x-facing electric field on the other side. The same thing in the y direction. Any component of the electric field in the y direction from one side of the sphere will be canceled out by the y component from the other side of the sphere. The only thing that survives is the z hat direction, which in the convention of IJK, Fedekai, this is the z hat direction. Yeah. Now, yeah. The real kicker here, from what I'm seeing, for what they like to say, is it's called Coulomb's. It's called the shell theorem, and this is what we've said, that right, if you are outside of a spherically symmetric charge distribution, that's the same thing as there being a point charge at the center of that spherically symmetric charge distribution. So let's look that up. 1 sec. I don't think I went over this during lecture. There's only so many things I can go over in an hour and 15 minutes. I've like mentioned it as like a trick we use, but I haven't like gone over it. Shell theorem, Coulomb's. Wow. Okay, the derivation looks like it kind of sucks. But it also applies to gravity, apparently. Oh, this is also cool, right? So, yeah, the gravitational field of, like, a big ball is the same thing as all of that mass being concentrated at the center of the ball. And there's probably a video on it. Let's see. 1 sec. Probably a cool video here. You assume infinite number of thin rings to make a disk. Okay.
Why is it every time someone says thin rings, I think of food?
Oh, dude, I want some thin rings.
Oh, yeah!
Some onion rings? I would fuck up some onion rings right now. This looks way too complicated for me. Dude, what's going on here? Excuse me. What are they doing? Okay. Oh, that's inside the shell. Oh, yeah. Well, inside the shell, of course. Yeah, that's... Okay. Maybe I see something here. Oh, I like an animation. I'm still trying to understand what's happening here.
Okay.
Yeah, it's too much. It's too much. I don't know. I can't do it. Okay, here's the trick, Fedekai, and this is what just if you want to take a deep dive into it, you can look up the shell theorem and try to find like a YouTube video on it that you probably watch for 30 minutes and you watch it like 40 times until it makes sense. If you're interested, yeah. I personally don't understand it, and I can't take the time to understand it right now. But what it says is that if you have, for instance, this has a charge Q1 on it, okay? And you're figuring out, let's say, for instance, the force on this charge Q2. This is the same as this Q1 being a very, very small charge located at the center of what the very, very big charge was. As long as you are outside the sphere. And this has to, and also you see this with Gauss's law, right? As long as the Gaussian surface encloses the whole charge, I don't care what the shape of the charge is. Well, I do care what the shape is, sorry. I don't care like how big the shape is. As long as it is still spherically symmetric, right? Such that the electric field points out this way. Well, let me make that a little bit better. Trying to make things that are normal, right? Yeah. So as long as your Gaussian surface encloses the same amount of charge, and that charge has the same shape, like it's still spherically symmetric, the electric field located here will be the same. I do know about Fourier transforms, yes. So here E1, and then we would say like is the same. This is the same electric field. It's because you can reduce any spherically shaped charge to a single point charge that's at the center. So in this case, instead of like thinking about this wacky thing that looks like this, right? It's a shell, right? That's located like this. This is like kind of like a side view profile of it. And you're trying to figure out the electric field here. What you can do good. All right, good, you're back. Is that you can reduce this to just a single point charge here. So if this has a charge Q1, this also has a charge of Q1. This is the same as this. As long as you are measuring things outside of the sphere. There probably is a rigorous way to go through and do a 3D spherical integration here with volume, and again have all the X and Y components cancel out so that you're just looking at the Z hat component. And I think how they do it is they do like a bunch of like, they call it like annuli, like a bunch of like little discs that they just like expand out. But don't hurt yourself. It's a lot easier to just use this, and then you get the same result. Does that make a little bit more sense, Fedekai? Yeah. Let me know. I agree. Yeah, what's up? What's up, Sensation?
Electrons just have mass that's so negligible. Are they ever affected by gravity?
It's the gravitational force of on electrons is very small compared to, say, for instance, the Coulomb force, which is the
strong force.
The electric force between things. Yeah, no. But then you have the strong nuclear force, which actually is important if you can get two electrons close enough to each other. or in this case, like 2 nuclei close to each other.
Right.
And that's what creates like atom bombs and stuff. Is because you start tapping into that energy once you can get things like really, really close to each other. Well, this is actually fusion bombs, is what this is, not fission. But yeah, yeah. There's a potential you have to get over.
Electromagnetism, gravity.
Yes. Yes.
Are they forced types?
Yes, there are 4 fundamental forces of the universe. I think it's the
Strong,
electro-weak, strong, weak, gravitational.
Electromagnetic.
4chan, no, 4 fundamental forces.
The first thing that comes up is just...
It's 4chan, no. Yes, this is it. Oh, E and M, strong force, weak force, and gravity. Yes. Those are the 4 fundamental forces. And this is actually a cool little diagram of this. So yeah, E and M, electromagnetism. That's what like has charges like attracted or repelled from each other. The weak nuclear force, I guess that has to do with bosons. You have the strong nuclear force. That's what keeps all the protons together within a nuclei. If you think about it, it's really weird, right? Protons are all positive. They technically should repel each other, right? Because positive charges don't like to be around other positive charges. But they are stuck together in a nucleus. And the reason for that is the strong nuclear force.
Well, the implication there is that then gluons have a charge as well. In opposing ways.
Well, it depends what so yeah, on the bottom thing here, they're talking about force carriers. So they're talking about what carries the effect of this force. So with E and M, it's photons. Like photons carry electromagnetic forces. It's bosons for the weak, it's gluons for the strong, and then this is where like gravity is a force. It has fields and it has waves. And so this is where they start thinking, is there a thing such as a gravitron? Like is there has to be some carrier for the force of gravity. But we don't know what it is yet. Gravitons or something, yeah.
I always thought the implication was that it was space itself.
Yeah, I mean, space is space-time. Yeah, wow. Yeah, if you want to see some hardcore physics stuff, and then here we'll do some other questions. There you go. These are how the forces are like defined. These are tensors up here. This is if you want to be a theoretical physicist, this gets you off. Like, you love this stuff. This stuff scares me. I don't like this. I like using my hands to like test things and build things and run circuits, but if you really like theoretical physics,
I wouldn't say it scares me, but it's certainly way beyond my scope.
Yeah. Can you make a Fourier transform for a triangle wave? Yeah. I mean, you can make a Fourier transform for anything if you have enough sampling, right? It's generally difficult to make things with rough edges and like hard edges and like straight lines, because what a Fourier transform is doing is creating a shape out of a bunch of sine waves, and you're varying the frequency, the phasing, and the amplitude of them to get them to add up and superimpose to create your shape. So naturally, it's easier to make curvy shapes out of curvy shapes. If you're trying to make straight lines, like bricks and stuff, out of curvy shapes, it requires a lot of them. And they have to be like really exactly like placed. So, you can. It's just not easy.
Next question.
Yeah, okay. Yeah, sorry. Yeah. Okay. Let's see. Ethan, you want to go over your question? You haven't asked a question in a while. I haven't seen you in a while. Is he still here? Ethan.
Looks like it is.
Here, let me tag him. I know he's been waiting here for like last hour. What's up, Green Pickle? Yes, I do remember you, Green Pickle. I do.
Must be at dinner.
Yeah, he's there. Mistral. What's up, Mistral?
I don't think the YouTube chat is loading in messages anymore.
Oh, it's not? Oh, my bad. Oh, very sorry. Wait. I think it. Wait, let me see. Test. Oh my god. Oh, yeah. It did lag. Thank you. Sorry. Okay. Yeah. It does that sometimes. Yeah. Okay. Now I got it. All right. Let me go through the chat real quick.
Okay.
Thank you for coming in and telling me that, though. Okay. You know how E's in terms of R hat, but since there's... Yeah, okay. Alright, one sec. Yeah, alright. Let me... Okay. What would you do about the radius? The radius is the same. Are you talking about this? I mean, here the radius would be very different, right? You'd have like a bunch of different R's. Like you'd have an R here, you'd have an R here. But once you reduce this to a point charge, you only have to worry about one radius, which is this. From the center of it. So in this case, R is just equal to 1.63. You actually don't care about this. And if you notice that, do you see how, like, because I have the instructor version, do you see how it says, like, the answer is calculated from this? Do you see how none of these variables got used? We didn't use R1, we didn't use R2. We literally just said, this is KQ over R squared. Where R is just the distance from the origin in the Z direction where you're measuring the electric field. Yeah, doing the integrals, you have to, like, do the sines and cosine terms. But the easy solution here is just to think of it as like a single little point charge. Yeah. Shell theorem. Good thing to learn. What's up, Hikaru?
Yo.
How's life, dog? Haven't seen you in a bit. How's your summer?
I know. I'm good.
Good, dude.
Finally going into high school.
Finally going to high school. Nice.
Yeah.
That's sick. What do you have planned for high school? I mean, well, I don't know. I didn't really have plans for high school. Are you going to play any sports in high school? That's kind of a thing sometimes, right?
Nah. I don't know yet, to be honest.
Okay. Well, just go into it with an open mind, dude. High school was like a very unique... You know, it's one of the most transformative times besides college in which, like, everything in your life changes pretty quickly. Also, some of my longest friends I made in high school. Yeah. And then we went to college together. So, I don't know. Be open for friendship. Is it... Yeah. How big is your high school? Do you know?
It has like 700 students.
Okay. That's decent size. I think mine in Texas was like 1,500. It was
it's not like crazy big.
Nice. Are you doing anything for the summer? Dude, the summer before high school, that's always like a little like last breath of freedom.
Yeah, I'll probably just go to the beach, to be honest, with my friends.
All right, hell yeah, beach is great. I went to the beach 3 days ago. I went surfing. It was really fun. Nice. Is this the question, Mistral? Is this it?
Yep.
Okay, cool. All right. Consider a uniform electric field in the gap with two oppositely charged plates. A single... Dude, there's too many words in this. But yes, okay. Negative enters the field with an initial velocity v minus straight to the right. The trajectory... Okay. Just barely missing hitting the positive plate as it exits device indicated. Next, a positively charged ion of the same mass enters the gap near the positive plate with Okay. Okay, cool. What must a relationship between V plus and V minus be? Okay. Dude, this is the smallest... Let me get a bigger image. Okay, there we go. Okay, now I can actually see this. Okay, let me get... That was too tiny. I couldn't read it. Okay. So, when you have... Why are they calling it VCL? What? Why are they calling it VCL? VCL minus? VC... What? What? VCI... Why? What's the C for? Okay. I don't know. I don't know what they're using that for. Okay. Okay. So if you have a negative charge here, right? As this thing moves in this direction, it's going to feel a force, right? From the negative charges here that is going to push it down this way, right? And so then as it's moving in this direction, it gets pulled down this way, and it so happens that the amount it gets pulled down is just so that it barely clears this, right? You could figure out what that force is, right? By figuring out what the electric field is. Which, yeah, should be constant, right? Isn't it? I think the electric field is constant amongst the whole thing here. Yeah. So, as this thing, it's you know what's funny? This actually acts like almost like gravity. This is kind of the projectile question, where you have something just being shot with a horizontal velocity, but then you have gravity pulling it down. But in this case, the thing that's pulling it down is the electric field. Okay. So, F is equal to QE. If this is a negative charge, right? So this is Q negative. So let's say for instance this is like negative E or negative Q. And then the electric field is positive, right? So that means your force is downwards, right? So your acceleration would be equal to negative QE over M, okay? And so, and that's strictly in the Y direction, right? You have acceleration of this thing strictly pulling down. So, if you wanted it to like barely clear this, right? Then, I think I want to do this. Yeah, okay. Let's say this is some gap distance, D. Or no, let me just call this Y. This is some distance Y. Let's call this distance X, okay? Then you would need, from this kinematics equation, Y is equal to Y naught plus V naught Y, V naught YT plus 1/2 AT squared. Okay, so the distance it would travel, so you'd say negative Y, because this would be 0, would be equal to 1/2, and then this would be negative QE over M T squared. Where T, right, is the amount of time this thing is traveling through the electric field. And that time is going to be equal to the distance X divided by what they call here VCL minus. I don't know why they're calling it that. So, notice here, right? The amount of time that this thing spends traveling through this electric field does not depend on the charge, right? It only depends on the velocity. But the amount it displaces does depend on the charge, because if Q is positive, okay, and this thing is starting here, then your change in Y is going to be positive. So this is why the charges have to be the same. So let's call this, for instance, let's say this is like negative Q1. Right? So this would tell me, okay, so Y is equal to 1/2 q1 e over mt squared. Oh, and this is the same as going up y for a positive q. And this is going down y for a negative q. Okay? Do you see, like, based on, like, whether the charge is positive or negative will depend whether the acceleration pulls it down or the acceleration pulls it up. And if it starts up here and it's negative, then it'll pull it down a distance y. So this would be negative, and then this is negative from your acceleration. But if it was starting here and it's positive, then it's going to go up by an amount y. And again, your acceleration will be positive because acceleration is dependent on q times the electric field. Yeah. Does that make sense, Mistral?
Yeah.
Yeah? Okay. Cool. I mean, that's a cool question. Why would it be like 1/2, dude? What? But all sorts of weird things here. Okay. Oh, Asta, I also did this one yesterday. Everyone's asking the same questions that I did yesterday. This one also took like half an hour for me to explain. Yeah, he's talking about this one. It's okay. I'm glad you're asking it because yeah, just go through the live stream yesterday. This one involves a trick where you talk about a positive Q charge here, or we say like positive rho, and then you superimpose negative rho on top of it. And then when you superimpose that, you get a hole. Yes, Reki, but the lecture stream is for teaching. This is for like asking questions. But yes, I will do y'all's questions. Because yeah, we have been doing physics for the last hour and 20 minutes at this point. I'll do more physics later, but yeah, let me yeah. So check this out. I have this in the stream there. Okay. So from yesterday, I'm just gonna start spouting off names, and whoever says they're here first. So we got Bob Ross's, 1K. Is 1K here? No. Okay. Next one would be Shantrix. Shantrix, you here? Shantrix is here. All right, cool. Let's do yours. Okay. Lurking in the shadows. Well, I hope you're learning some physics along the way. You know, might be a little preview. Okay. In the diagram, rectangle PQRS is placed inside a rectangle ABCD in two different ways. First with Q at B and R at C. Second with P on AB and Q on BC. Okay. Oh, I see. Is it the same rectangle? Determine the length of BC. Okay, cool. Interesting. That's really cool. And they give us AB and they give us PQ. Oh, nice. Okay, so they give us this and they give us this. Oh, okay. So that tells me this is then, and then what am I looking for? Sorry. Determine the length of BC. So they want to know this. Thanks for the follow. Oh, we hit 1700 recently. Nice. Yeah, we're already at 1704. Just keep going up. Good.
Hoomst.
Like and subscribe. Hoomst.
Hoomst.
Hoomst. 4S2 Tony. What's up? Okay, so this one is 250, right? And then this whole thing is 718. Okay, does anyone see like a trick here real quick? I'm trying to see what we got. I want to say it's like similar triangles or something. It always is.
I just want to wait for the right person to follow the channel.
4S2 Stony. 4S2 Tony. Oh, ooh. Wait a minute. I think I have a key here. The area of A and the area of B have to be the same. Ooh, I think I see something. Right? This still has to equal this. Yeah? I feel like that's something cool. So
Is there not some obscure rule about rotating a rectangle and a square?
no, I don't think there is. Okay. So area A is equal to 718 minus 250 times x. This is what we're solving for, x. And area B is equal to 250 times x. Okay. And that has to be the same for here. Oh, you know what that tells me? That tells me that this distance is the same as this distance, right? Oh. That's cool. I like that. Right? Okay, so now I know that this is x. And this is also x. Oh, okay. Shantrick says you can get BQ. I'm not sure how you do that. I'm also going to argue that this must be symmetric to this, and this must be symmetric to this. So this plus this must be half of this. What's up, Fizzbuzz? Good to see you, bro. Is PB in the second diagram equal to PQ in the first? Is PB in the second diagram equal to PQ? No. I don't think so. Oh, is it the same point P? Yeah, wait. Is this the same as this? That is a good point, actually. I don't know if we can say that is true.
I don't know, split PR, and then you've got just a whole thing of triangles.
Yeah, I don't know. I don't know that. I don't think. BQ would have to be 0 by the Pythagorean theorem. Yeah, correct. Yeah, that wouldn't work, right? Yeah, okay. Okay. I'm gonna define one more variable. I need one more variable. I'm gonna call this y. Y is gonna refer to this. I'll show you why. I'll show you why I need it. Okay. Cause now to get the area of the red sector, right? I can figure out what this is, right? This is now gonna be the square root of x squared minus y squared, right? So 1/2 square root of x squared minus y squared times the height, which is y. That's the area of this. Plus the area of this, which would be, and I think we have that, right? We know AB is equal to 718, right? So that would be 718 minus the square root of x squared minus y squared. Right? That's what this little chunk here is. And that's 1/2 base, and then the height of this is now x minus y. Uh-huh. Okay, and then all of that times 2 has to equal 718 minus 250 times x. Okay? Now, I have too many things here. I have like x's and y's, but I know that this is 250, so this is actually something cool. So, by the Pythagorean theorem here, right? We said before that this is x minus y. So I know that x minus y squared plus this, which is 718 minus the square root of x squared minus y squared squared. This squared plus this squared has to equal 250 squared. Yeah? Okay. Let me see if some things cancel. 2's a cancel here. Uh, 718 minus 250 is 450, 468. Okay. And then this statement's also true. This looks kind of similar to this.
Having a hard time with that question.
Oh, yeah. This one's kind of a pain. What's up? You're back, Ethan. I was going to go over your question.
I was just doing some stuff.
Oh, it's okay.
My bad. I was just out.
Here, let me punt on this for a second. Yeah, let me help your question real quick, just so I make sure I do it, because I know you haven't been here in a while. But we're getting close on this.
I don't think it's that complicated compared to others, right?
I don't care. I mean, honestly, I love it when things are like a little bit less complicated. It helps my brain out. Okay, here we go.
Then.
Oh, this is actually not very simple. This is relative velocities. Okay. I might mess this up. Okay.
Okay.
You're trying to row a boat directly across a river that is 50 meters wide.
To be honest,
You can...
there is no pressure in this. I mean,
Uh-oh. What's happening to your audio?
like there's.
It's kind of a cool one. This is 50 meters wide. You can row at 3.1 meters in a direction directly across the river. The current is 4.8 meters per second parallel to shore. What is your velocity relative to the shore? Okay. I sometimes screw these up though. So I feel like this is 3.1 meters per second. But then the river is 4.8 meters. Okay, you're good. And then yes, Nick, I'll help you out. Okay, 4.8 meters. So then this is like... But here's the question. I think sometimes like this is the 3.1. Is this the 3.1 or is this the 3.1?
Can you hear me now?
Yeah, we can hear you.
We can hear
Okay,
you, Ethan. You're
thank
good.
I was just using headphones. Like, literally just got headphones like yesterday while I was in DOS.
Oh,
But
okay.
I tried. It's not working as expected. But I'll take them. I'll still use them.
Good, good. Okay. What is your velocity relative to the... Oh, this one's... Okay, so velocity relative to the shore, right? So this is... Do you see what this is? This is a triangle, right?
Yes.
So I think we just do Pythagorean theorem here, dude. Right? I think I just do like 4.8 squared plus 3.1 squared is equal to like... This is like... V relative to the shore.
V short then? Or VS? Just do
VS. Yeah, let's just do VS for now. Okay, let me pull my calculator out. 4.8 squared plus 3.1 squared equals that. Square root of that. 5.7. Nice. Yeah, that's 5.71. We got that. Okay, so V shore equals 5.71 meters per second. And then if you want the angle, you just take the arctangent, right? Of opposite over adjacent.
Arctan?
Yeah. So,
Alright.
remember that, right? This is a right triangle. And if this is an angle theta, then this is the opposite, and this is the adjacent, yeah? So the
Yeah.
tangent of theta is equal to the opposite over the adjacent. So that's equal to 4.8 over 3.1. But then if you want to get theta, take the arctan of both sides.
So
This
that's
cancels?
like multiple. That's like taking it's like you're reversing tangent,
Yes, you're reversing tangent. That's what arctan is.
and then
4.8 over 3.
4.8.
Good. And then that gets you 57 degrees. So this is 57 degrees. But look, they want the answer, they say downstream from the shore. Okay. So they're saying like from the shore. Okay. Well, then this amount, you know, has to all add up to 90. So this must be like 23 degrees.
That's it.
Or no, sorry. Not 23. I'm really dumb. 33. Yeah. Cool. And
that's the whole
then
thing.
how far downstream do you land? Or how much time does it take? Ooh, interesting. Well, you only care about the 50 meters, right? So I think the time is just equal to the 50 meters divided by 3.1 seconds. Because this is meters per second.
Meters per second.
Sorry. I don't know why I'm saying 3.1 seconds. Sorry. 50 meters. 50 meters over 3.1 meters per second. That'll get you seconds.
Mhm.
And yeah, that should be 60.1.
60.1 seconds.
Yeah, 16.1 seconds. Nice. And then how far downstream do you land? Okay. Well, as your boat here, right, is trying to go this way, it's also moving this way, right? So the amount of time you move here is the same amount of time you're going to move down, because you're really doing this. So for that, you just take this velocity. So you take 4.8 times the 16.1, and yeah, that's 77.4.
How do you do that so quick? How do you do that so quick?
77.4 meters. Yeah, we did it. Good job, Ethan. Yeah.
How did you understand? How did you know how to do the multiplication?
I did it with a calculator.
But you set it up before the calculator even solved it.
Oh. Well, also I knew what the answer was. They give it to you.
About what?
Ethan, they give you the answer right here. They give it in bold.
Oh. Alright.
Okay, nice. Good job, Ethan.
It's been such a long time since I asked that question. This feels nostalgic.
Are you going to college? What's up? What are your plans now, dude? I know it's the summer. You're working a job at like a store. What are your plans after this?
Well, computer science, if you can remember. I have my diploma. I
Nice.
still plan to study that and plan to go to Taiwan since they have much more advanced technology.
Taiwan?
Uh-huh.
You're gonna go to Taiwan? That's pretty dope.
That's dope.
You're gonna go to Taiwan for college?
No. I'm going to do college. Then,
Oh.
if I am ready, then go to Taiwan.
Oh, okay. That's cool. Yeah, they have a lot of like
That's
semiconductors and stuff there.
But I'll have to study Mandarin since they speak that there, and that's like the hardest language. Arguably.
Yo, wait, isn't like Belize like partially owned by the Chinese?
Really? It is? I mean, I see products that have made in China.
Well, I mean, yeah, everything's made in China these days, but no. But no, I think Belize. I think China has heavily invested in Belize.
What are you talking about heavily invested in?
Why are all the stores owned by Asians in Belize, dude? What's up with Reddit, dude?
Yeah,
Oh.
we have Asians that have. There are stores that have Asians in them.
I'm sure. I thought when I was in Belize that I remember there being like a lot of signs in Chinese, and I was really confused. I was like, wait, why is everything in Chinese here? We're in Belize. We're in like South America almost. And then I think it's because China gave a lot of loans and grants to like develop their ports. And maybe I'm wrong. I thought it was one of those countries where like China has a lot of influence, which would make sense. But then actually it wouldn't make sense with Taiwan because China and Taiwan aren't really friends. Okay.
Taiwan is the real China.
Can I tell you two things before I go?
What do you want to say before you go? Yeah, what's up, dude? And then Riker will do your
There's one
question.
thing, though. Okay, yeah. But you know how like there are placement exams?
Yes, like AP exams or like placement in college to like take classes exams.
Placements in college, yeah.
Okay, what's up?
So I just did mine this year, and when I got back my results, I passed math with little to no difficulty. Like there was no
Okay.
troubles in it. But then,
Yep. Placement exams should be
when it came
easy
to-
for you.
But when it came to English, I failed that.
Oh, don't worry about the English. You know, I mean, it is important to know English. And Sensation's gonna get mad at me here if I'm saying don't worry about the English. But you should know English.
I don't worry about the English.
Listen. The thing is that it's like, if I had passed the ad-lib, I would have been with everyone else because literally everyone I've asked has gone into the higher English level to where I am right now. And I couldn't even do summer school because I had to get to the US. So it's like, I'm literally behind on school then.
It's okay. You'll catch up, man. And like, I mean, enjoy your time in the US. That's a rare thing, especially, I don't know, with how things are moving. I don't know how much easier it's gonna be for like foreigners to like come to the U.S.
I mean, hey, I could still take some till next year and catch up, but
Yeah.
it would have been cool if like I was with them right now. I didn't even have to worry about summer school. I don't know.
That's true. I think you'll be okay. You'll be okay, man.
I'll keep you.
Enjoy your time in the U.S. Yeah. Let me know if you come to
For
Los
sure.
Angeles.
Can I show my face cam really quick? Can I show
Yeah,
my
you can
face
show your
cam as
face.
well?
Yeah, come. Yeah, come. Show your face. Show your face, Ethan.
Like,
There you are.
I'm done.
What's up, Ethan? Good to see you, bro.
hello. I also wanted to show you this cool thing as well.
Yeah. What do you got? What do you got?
This is this light thing. See?
Whoa! Game on. Oh, that's cool,
Whoa.
man. Oh,
What is
what? It
that?
changes colors. That's sick.
Yeah.
That's dope.
I'm going to put it to test
That's
as soon as I
really
get to
cool.
my. I'm going to put it to test once I get to my house. But in the
Yeah.
meantime, I just stare at blackness for now.
Okay, that's cool, Ethan. That's cool.
But these are one of the things I got just yesterday.
Just being in Denver, right? Because you're in the United States. Yeah, that's cool, man.
Yeah.
Go eat some Chiba Hut. Have you been to Chiba Hut before? It's like the sandwich shop.
I don't know that place.
Yeah.
Chiba Hut?
There's a Chiba Hut. Go tell your parents or something. Be like, yo, we gotta go to Chiba Hut. They got really good sandwiches in Denver there.
All right then. But there is one last thing.
What's up? What's up?
Do you remember how I would tell you that I had an ex before?
You did have an ex-girlfriend. I remember we were going through your girlfriend troubles last year. Yeah.
Damn.
Yeah. But like if you didn't know, that
Yeah.
it was like it marks 1 year then since I first met her. When I first met her. So just
Okay.
last year was my first meeting her. You know what I mean?
Yeah.
Nice.
Time goes by for sure, man.
Yeah, I can't believe it. Just a year ago, I was in Belize and just starting my job. Now look at where I am.
Yeah, that's cool. Now you're in the United States. Yeah, it's really cool. Enjoy all the moments, Ethan, is what I say. You know, it goes by quicker as you get older, so enjoy it while you have it, you know. Have fun with it.
Honestly.
Okay.
Also, there was one last thing. One last thing.
One
that's
last
related to
thing.
my question.
One last thing. Okay, what's up?
Are there like those empty coins that you said, or you don't give them for questions anymore?
SCP coin or SCP. Yeah, we will give SCP coins. Register for the tournament. Make sure you do that. I'll give you the coins for it. I
How
gave
do
you a bond
register
coin.
again?
It's
How do I read?
just check it's in the announcements tab. Look in the announcements.
Ping you.
He'll ping you.
I'm trying to ping you.
Nick will ping you. Okay. Okay. Let me quickly do Recky's question because I gotta go teach in a little bit here. Cool. But good to see you,
Yeah.
Ethan. Okay. Recky, you here? I know Recky's here. Consider the function as such. Determine the zeros of the function after each transformation. Okay. What are the zeros of the function right now? Should be able to do this, right?
Hold, I have a question.
What's up, brother?
Is nursing a good major
Yes.
in
It is very
college?
good. Yes. We will always need nurses.
I'm thinking of it. I don't know.
Yeah, nursing's cool. A lot of hot girls in nursing.
What
A lot of fun, dude. I mean, it is very much a heavily female dominated industry for sure. I have 5 sisters and like 2 of them are nurses. Yeah.
Damn.
So, yeah.
How's the studying and stuff?
It is difficult. I mean, you definitely got to put in the time. It's not a cakewalk, but it's not super hard. If you put in the effort, you can do it. I think nursing school isn't impossible. Yeah. And they have so many different nursing schools. So like you can go to one like at, you know, a formal like 4-year college, or you can go to like specific like nursing schools which are like smaller, and they even have like online ones too. Yeah.
Thinking of going for a 2-year in
CNS.
Kingsborough. I don't know if you heard of that.
Yeah, I haven't specifically, but it's called like a CNS, like certified nursing, whatever, something. CNS degree. Yeah. No, it's a great career path. It's very secure. We'll always need nurses. Just keep in mind, it is kind of brutal though. You know, you work like really
Right.
terrible hours sometimes. You get paid for sure. But you know, maybe try shadowing or like seeing what a nurse does, because you have to like do some pretty gross stuff sometimes. My sisters tell me stories. I'm like, oh no.
Oh God.
Yeah.
Oh,
So
no.
just maybe just make sure that's okay before you invest all this time into like becoming a nurse.
Right.
It's a pretty demanding thing. Yeah, that's what I would say.
Mm-hmm.
Okay. All right, here. Let me do Recce's real quick because I want to help you out, Nick. And I have one kid. I got a bunch of people here. We're gonna get through everyone. Okay. Zeros of this function are at -4, good, and they're at 3. All right, and then this is a quadratic, so it probably looks something like this, right? Okay, so we want to ask ourselves what happens to the zeros after each function. So what type of transformation is this, Recce? So where you take the function and 4f of x, which means you multiply everything by 4. Does that change where the zeros are? Oh, this camera's fine. I see it. So 4f of x would be equal to 4x plus 4, x minus 3. Does that change where the zeros are? Does that change what causes this to be equal to 0? No. Good. The reason for this is a vertical stretch. So all you're doing is you're just like stretching the thing out vertically, but they're still going to hit there. Okay. So it doesn't change them. Good. F of negative x. Ooh, okay. So f of negative x, that's going to equal negative x plus 4, and then negative x minus 3. What do you see that did to the zeros? Now what do I need for... It does change the zeros, yeah. Because now -4 doesn't work, right? Now I need +4, right? Because if this is +4, then -4 plus 4 is 0. Good, yeah. So it switches them, or flips the sign. And the reason why it does that is this right here. This is a flip over the y-axis, okay? So this like puts this over here, puts this over here, and so that's going to switch where the zeros are. Okay. What does this one do? This is the same thing as a horizontal stretch. And then this is going to be a horizontal compression. So it's actually pretty cool, right? So if you had, for instance, f of 2x, right, is equal to, this would then now be equal to 2x plus 4, 2x minus 3. Now do you see how, like, oh, I only need x to be equal to -2, not -4. And here I just need x to be equal to 3/2. What's up? That is what the 1/2 is. So the 1/2, if it's, so look, so f of 1/2 x, that's equal to 1/2 x plus 4, 1/2 x minus 3. So now you need twice the x, right? So instead of -4, this has to be -8 in order for this to equal 0. So that's why this is a stretch. This stretches it out, and then this one compresses it in. So the zeros either multiply by 2 or divide by 2. Nice. Cool. Good question. I like that. Chantrix, I'll still give you a point, because we did do your question at least, but I want to make sure I help out. Nick, you've been waiting for a while. Let's do a couple yours, and then 1K. If I still got time, I'll help you. All right, let's see. Which ones did we do, Nick, last time? We did 3 of them, didn't we? Sebastian Lopez, what's up, dude? Wow, amazing. Amaze God.
I'm in the middle of a game. Shit.
Oh, okay. Do you want me to skip you? Do you want me to skip you? I can do 1K's question if he's here, and then I can do you afterwards. I need to go in like 30 minutes. So finish your game in 30 minutes.
Oh. No, I have 5 minutes to finish the game.
Okay. Finish in 5 minutes. I'm gonna help 1K, and then I'll help you.
Okay. Okay, cool. Thank you.
Cool. You're good. What's up, 1K? 1K, you round? Where's 1K?
Just keep abusing the poor bastard.
Keep abusing the what?
I said I just keep abusing the poor bastard. Every time he just jumps in, and the first thing he says is WSP, so it's just like I'll just spam that.
Oh,
Gen
I see.
Alpha
Yeah, he said, haven't you said that to me before? What's up?
Like, and I'll fucking say it every single time with me saying hello.
Hello.
Like a normal fucking.
Hello. Yeah, what's up? What's up?
I'll even settle for Ayub Gadji at this point.
Ayo, Gaj. All right. Well, while I wait for 1K.
How is he in there?
Let's see if we can still do this one that Shantrix gave me. This one was kind of a pain. I gotta tell you, Sensation, my uncle, who lives in Cambridge, keeps sending me screenshots of how much he spends at Spoons for breakfast, and I'm horrified by how cheap it is.
£7? That's how much it used
Dude,
to
like
cost,
£2.
right?
Like 2.
What's he buying?
Dude, I'll show you. It's insane. Oh, there's 1K. Okay, good. 1K showed up. All right, 1K, what's your question, dude?
Spoons is pretty cheap and nasty though.
Here, I'm gonna send you. Dude, they're so cheap. What? Let me go find it. It's my Instagram. Oh, this is my actual education Instagram. Oh, damn it. I sent it to the wrong one.
Damn it.
Damn it. There we go.
Let's all go meet in Albuquerque.
Albuquerque's pretty dope. I used to work in Los Alamos. I did a summer physics internship there. Okay, here we go. We got some pictures.
For a split second, I forgot that Los Alamos is in New Mexico.
Yeah, dude. Okay, so here we go.
Wait a minute.
Yeah. Apparently, these are the deals, dude. Small breakfasts, $2.79. Dude, what?
Yeah.
This is so cheap.
8 a.m. That's quite late.
8 a.m. to 12. And then this is apparently his... He got an egg and bacon muffin for £2, 2 mushrooms for £1, orange juice. And then there was a promotion applied. So he only paid £4 for breakfast, dude. Bro, like... can't buy you anything here.
I'm back.
Oh, you're back? Okay. Cool. Alright, what's up, Shaq?
Yo, can you hear me?
I can hear you, dog. I can hear you this time.
Alright. God damn, I got these new headphones. I was gonna tell you, right?
What'd you
'cause
get?
I was thinking about you, right?
Didn't I buy you headphones at some point,
Remember,
bro? I did buy you
You
headphones.
bought me headphones like 4 years ago, something like that.
I did.
3 years ago, I think, right?
Well, I didn't. You
And-
won them. You won them in a contest, but yes, I did buy them.
All right. Right.
Thanks.
So after all that time, about a month ago, it finally got like messed up.
Okay. Wow.
So
The
I
legacy,
bought a
dude.
new pair, right? Yeah,
Nice.
right. I bought a new pair. I bought like some stuff, you know what I'm saying? Some like, now that I thought of it, I was like, I'm gonna play the summer camp because that was like one of the first things I won, right? Not
You
for
did.
the summer camp. I remember summer camp I won.
It was one of the tournaments.
Cold War.
Yeah, Cold War did. Yeah. Yeah. That's dope. What's up, Fembox? Yeah, we're gonna do. I'm out of town this weekend with a wedding. But next weekend we might do like Fortnite or Roblox or something. If you want to come play, I was playing Fortnite with people last weekend. Taco Cat did pretty well actually. Wait, let me get one extra shit.
I can't play.
Okay, Nick, let's try to do this one. Suppose that 10% of those who commit serious crimes are convicted, and that 15% of those convicted are sentenced to more than 3 years. The percentage of those committing serious crimes who are sentenced for more than 3 years is what percent? Ooh, okay. This is kind of cool. So here we you get it. These ones are kind of, you want to like build like boxes around this. So here, let's do this.
I did 10% of 15%, but I got like,
Yeah.
I think it was point.
No, you're
I
right.
don't know if I got it correct. Or
No,
I
it
didn't
is.
get it
It's 10% of 15%. Okay. So convert percentages to decimals. That's 0.10. This is 0.15. If you multiply these together, you get 0.015. Which should be answer choice D.
Let me check. I don't think that's correct. That's what threw me off. Cause, give me 1 second. I think the answer is B.
Oh, the percent. Oh, sorry. This is 0.015, but then as a percent, that's 1.5%. I forgot. Yeah. What's up, Stonks Investor? Yeah, the key thing here. So usually, I don't know. This is kind of lame, but because they say percent, you need to multiply this by 100 again. Yeah. Okay, that's why it is. Wow, that's tricky. Okay. Let's do another logic question here. And here, let me download this one for you. Nick, number 9. Okay.
942.
Assume there are 1,100 employees in a city agency. Of these, 15% are officers, 80% of whom are attorneys. Wait. Excuse me, what? Of the attorneys, 2/5 have been in the agency more than 5 years. The number of officers who are attorneys and have over 5 years of experience. Oh, okay. So is it just multiplying all the percentages together?
I have no clue.
I think it's 0.15. That's interesting. 80% of the officers are attorneys? Seems like a lot of attorneys to be officers. And of the attorneys, 2/5. So 2/5 is right this. The number of officers who are attorneys and have over 5 years. Okay, so it's all this together, right? So this is 0.15 times 0.8 times 0.4. Okay.
Nice.
So that's 0.06 times 0.8, which is equal to 0.048. And then this times 1,100 will get you the number. And that's, yeah, that's around 53. Answer choice should be B. Thanks for the follow, Linanoli.
For number 9, yeah, it's B.
What about for 10?
10 is B also.
Nice. Okay, cool. Save that one for you.
Yeah, for number 10, I did 110 times 0.15, then 165 times 0.8, then 132 times 0.4.
Yeah, that's fine. Did you get 53?
Yes,
Good.
52.8. But yeah.
Okay, that's basically 53.
Yeah.
Okay, here. Let me do one last one. And then 1K, I'll do your question. Okay. An employee who has 500 cartons of supplies to pack can pack them at a rate of 50 an hour. After this employee has worked for a half hour, he is joined by another employee who can pack at 45 an hour. Assuming that both employees can maintain their respective rates of speed, the total number of hours required to pack all cartons is... Oh, dude, this is a super tricky question. Oh, man. This is like the... If I can mow a lawn, but like 2 people can mow the lawn.
45 plus 50 and then divided by 500.
Really?
Plus the
No,
half an hour.
Well, okay, well, yeah, plus the half hour, right? So... So really, there's only... So after a half hour... There's only 450 left, right? Because the guy doing it at 50 an hour... Oh, 50 an hour, sorry. So, no. There's 475 left. Because 1/2 of 50 is equal to 25 done.
Yeah.
In a half hour?
Mm-hmm.
Okay. Yeah. So then... Do you just add the rates here? I feel like you don't.
I did 45 plus 50 and then divided by 500 and I had like 15 left. So you would have to add another half an hour, so another like 25. So it would take in like 4.5 hours or 5.5 hours.
Yeah, I don't think that's exactly the right way to do it.
Well, that's how I did it. I got it right.
Well, I mean, yeah, a broken clock is right twice a day.
Wait, that actually is funny. What the hell?
Okay, yeah, you do just add them together. I remember there's something. I remember there being something that if like if 2 people are working together, the rate is not just linearly adding the rates. Okay. Okay. So, yeah. So then you have 45 plus 50, so that's 95 per hour, right? So then you're doing 475 divided by 95. He says I think it's 475 because I think he does 50 per hour and the employees only worked for a half hour. Yeah, right? Okay. Okay, so this is equal to 5. And then you have the other half hour, so it's 5.5. Yeah. What's the question though, Femvox, bro? What's the one where the rates don't add linearly? Oh, I remember what it is. It's, you say like, if Dave can mow a lawn in 1 hour, but Charlie can mow an hour in 3 hours, like, how many lawns can they together mow in like 4 hours? That's what it is. Yeah, there's some weird one there. It's when they don't give you the rate, but they give you like the amount of time it takes for them to do one thing. Yes, there you go. Fembox says, I can paint a wall in 2 hours. You can paint it in 3 hours. How long to paint it together? Yeah. Yeah, man, that's the one I'm thinking about.
That's weird.
Yeah, it's a weird one. Yeah. That's what I thought they were asking you here first. Okay, cool. Good job, Nick. We did 3 more questions. I'm happy. If we keep doing 3 like every day, we'll get all of them done, you know.
Yep.
Nice. Okay, last question of the day I think comes from 1K.
Tomorrow you're here, right?
Yeah, 5 o'clock.
Okay, cool. Thank you.
Right. We paint 1/2 plus 1/3 in 1 hour, and then you invert it, right? Is that what you do? Yeah, Femvox has it. That's totally how you do it.
Can you send me the what we did?
Oh, the last one we just did. Yeah. I put it in the chat. Oh no, I didn't. Oh, I'm so dumb, dude. What? Why did I just send you this? What is that? That just sent you the answer, dude. What? Excuse. Oh my god.
I like how you said the same one.
Yeah, you know what it was? It's my copy paste was messed up. There we go.
WGU has a ton of resources.
Oh, we got an ad? Dude, what? I have not gotten an ad on this channel in forever, dude.
They transferred over, and because we can accelerate, I finished very quickly. With WGU, you can start whenever.
Good job, WGU.
For me, every time I turn on your stream, I get an ad right away.
On Twitch or YouTube?
Twitch.
Yeah, I think there's always ads, yeah. But there's no ads during the stream, though, right?
On Twitch, you mean?
Yeah, like in the middle of the stream. I don't think there are ad breaks. I think I got rid of those.
Middle, I don't think so. I don't know. I haven't watched it that long, so I wouldn't know.
Yeah. Okay.
But on YouTube, I don't think there's ads at all during stream.
Yeah. Okay. 1K. Let's try to do this one. A ball is dropped from a height of a 40-meter tall tower. You're welcome, Nick. Oh, I only have the pre-roll. Good. Well, I just don't want to bother students like while they're watching. Like, have to deal with ads. It's dumb. Also, I don't get paid anything from them really. It's like doesn't really make much money for me. Okay, and then this is 40 meters. What will its velocity be after covering a distance of 20 meters? Oh, this is cool. What equation do we use for this one? 1K. This is a good kinematics question. Oh, you said, oh, thanks, Fembox. That gets me $2.50. Jeffy Bezos paying my water bill, I think. You don't know what it is? Okay, that's all right. I mean, you honestly, you want to just like know these things. Don't spend it all at once. I won't, promise. Okay, so out of these ones, which one you want to use? I'm working out while watching the stream. Okay, we'll stop working out for a second. You have to learn. Yeah. The whole point of this is for me to teach you, not for me to just like mentally masturbate doing questions. Second one, not quite. Because, okay, whenever you're given these types of questions, man, look at what you're given, okay? So, top of a 40-meter tower, after it's covered at a distance of 20 meters, right? That tells you what delta x is. I know delta x is equal to minus 20, okay? If it's dropped, that tells me VI is equal to 0. I'm trying to figure out the velocity of it. That's VF. And the only other thing that we know is that if something is dropped in the air, it has an acceleration. What's that acceleration equal to? Yeah, initial final velocity. Good. Not quite. Acceleration is negative 9.8. If something is dropped, anything that's called being in free fall, which means gravity tries to pull it down at 9.8 meters per second squared. The initial velocity is 0, but the acceleration, anything that is in the air and is like not being touched by shit, doesn't have rocket boosters or whatever, always has an acceleration of negative 9.8. Pulling it down. That's what causes shit to fall. Okay. So given this, right? Which one of these equations, like, involves all these things? The second one? Well, this one has time. Do I have time here? I don't have time, right? It actually has time in 2 different places. I don't really like that, right?
Oh, no.
No. Yeah. Second one has time. I don't want to deal with time. Third one. Yes. Yes. This is called the timeless. This is timeless equation. That's what we call it. So we want to use this one. Okay, so now we just plug shit in, right? So I say VF squared is equal to VI squared. So that's 0 squared plus 2 negative 9.8 times delta X, which is the change in the position. That's negative 20. So you get VF squared is equal to, what is that? 392 maybe? I feel like that's 392. Maybe I'm wrong. 0.2 times 4. Yeah, 392. Okay. So then VF is equal to the square root of 392. Which you gotta do a little calculator here. So that gets you 19.79 meters per second. Okay, cool. And that's also down. You want to make sure you say negative 19.7 meters per second. Because the thing is, you know, going down. Whenever you take this square root, it'll only give you positive numbers. But you have to be smart afterwards and be like, oh, well, it's negative. It's going down. So when striking the Earth, what's going to change in my situation here? What changes when I'm no longer looking at when it's 20 meters down? I want to know what the velocity is right before it strikes the Earth. Yeah, that's okay. Overthinking happens all the time. Yeah, when it hits the Earth, yeah. Some students are tempted to say that the velocity is 0. And I mean, yeah, technically when after it hits the ground, the velocity is 0. The acceleration does not change. And whenever they ask these types of questions, 1K, we're asking like right before it hits the ground. Like right when it's right here. Not when it hits the ground, like right before it hits the ground. I know when it hits the ground, it's stopped. That's true. But a thing you learn in physics is that when they ask this, they shouldn't say on striking the Earth. They should say like right before it hits the Earth, not after it hits the Earth. It's weird. But yeah, only one thing's going to change here. The final velocity will change. Yeah, what we're solving for. But what out of my variables will change? Acceleration won't change. The initial velocity is still 0. It's still being dropped. The final velocity is what we're solving for. What about this delta X? Oh. Distance becomes less? Why does distance become less? The height? Yes. But it travels further. So originally we said, what will the velocity be after it's covered a distance of 20 meters? So when it goes from here to here, that means it's covered 20 meters. But now we want to know what happens when this thing has come down and hit the ground. Delta X always refers to the change in the position. So originally, when it was starting at the top and covering a distance of 20 meters as it fell, that change in position was negative 20 because it was going down by 20 meters. How far is it going to go down if it hits the ground? Another 20, good. So yeah, it turns out the total delta X here will now be negative 40. Okay? So here, you're just going to put negative 40 instead of negative 20. That's going to change this to 784. So then VF is equal to the square root of 784. And that's going to get you 28 meters per second. So, I mean, this should make sense, right? It's going to be faster when it hits the ground, right? When it falls all the way down versus when it's only dropped 20 meters. And notice that it's not double, right? It didn't go from 20 to 30. It didn't go from 20 to 40. It went from like 20 to like 28. And that has to do with the squared nature of this thing. That's why it's like square root of 2. But okay, good. Good job. Okay, cool. I gotta go teach another student. Let's try out the screen. You're welcome, dude. Alright, thank you everyone for coming to office hours today. Appreciate everyone asking questions, all the fun stuff. Yeah, I want to go over that tomorrow, Shantrix. I'll go over that. I want to go over that rectangle question. I feel like there's probably some nice easy trick to it. Always is. Alright, our next stream is going to be tomorrow. That's at 5 p.m. Pacific, 6 p.m. Mountain, 7 p.m. Central, 8 p.m. Eastern. Come on by. Get some help. Math, science, physics. We'll do it all. Let's go raid somebody. Who's doing some stuff? We didn't finish the rectangle problem, Femvox. I'll do it tomorrow. I want to finish it tomorrow. There's actually a lot of people streaming. This is cool. Let's go say hi to Nerduino. Nerduino's cool. He's watching like a launch or something. Yeah, dude, the rectangle problem was cool. We will do this. Because I guarantee you I'm like overthinking this. But we'll do it on tomorrow's stream. I got like kind of far on it, and then like this is just me like brute forcing it. Okay, cool. All right, let's go say hi to Nerduino. Enjoy the rest of your Tuesday. We'll see you Wednesday. Peace.